When we think about AI, we often picture it finding a path, from point A to point B. But what if the goal isn't the path itself, but the destination? What if the real challenge is to find the single best place to land out of millions or even billions of possibilities? Well, today we're diving into optimization problems, where AI's job isn't just to find an answer, but the absolute best one.
Think about using Google Maps. It's finding you the fastest route, right? That's a classic search problem. It's all about the sequence of actions, the turns you need to make to get to your goal. But what if the problem was completely different? What if, instead of finding a route, your job was to find the one single best place to build a new hospital for an entire city? That's optimization. See, it's not about the steps to get there. It's about the final state, that one perfect spot.
And this slide really nails the difference. Over on the left, you've got classical search. It's about the journey, figuring out the twists and turns of a maze. But on the right, you have optimization. That's all about the destination, finding that one X marks the spot that represents the absolute best possible outcome. Okay, so let's jump into our first big idea here, choosing the best option. What does it actually mean for an AI to sift through countless possibilities and land on the single, number one best choice? At its heart, an optimization problem is just this. You have a whole universe of possible solutions, and your job is to find the one that either maximizes something good, like profit or efficiency, or minimizes something bad, like cost or travel time. Simple as that. To really wrap our heads around this, let's use a classic example. Imagine you've got a city grid, maybe 4 houses, and you have to build 2 new hospitals. The goal? Place them in just the right spots to make the total travel distance for everyone as short as humanly possible. I mean, where would you even begin to figure that out? Well, one of the most intuitive ways to tackle this is a strategy called local search. The idea is actually really simple. You don't need some grand master plan. You just start somewhere, and then you start climbing, one tiny improvement at a time, toward a better solution. This logical process has a great name, the hill climbing algorithm. And here's basically how it works. First, you just plop your hospitals down randomly on the map and calculate the total travel distance. Let's call that your cost. Then you look at all the neighboring spots. What if we moved one hospital just 1 square, up, down, left, or right? If any of those moves lowers your total cost, you do it. You make the move. And you just keep repeating that, always taking the small step that improves your situation, always climbing the hill until you get to a point where no single move can make things any better. It sounds almost foolproof, right? Just keep making things better. But here's the million-dollar question. What if the easy, obvious improvement right in front of you actually blinds you to an even better solution that's just a little further away? And this is the classic trap of the local optimum. Picture this. You're a mountain climber in a really thick fog. You climb, and you finally reach what feels like the top of a hill. Every direction you look is down, so you must be at the peak. But what you can't see, hidden in the fog, is a much, much taller mountain nearby, the true summit, the actual best solution. The algorithm gets stuck on that little hill, a good solution, and it never even knows the best one exists. This quote just nails the problem, doesn't it? Hill climbing is fast, it's simple, but by always grabbing that easy, immediate win, it can totally miss the grand prize. So how do we solve problems where good enough is not good enough, and we have to follow very strict rules? Well, that brings us to our next method, which is built specifically for problems that have hard limits. This is all about finding the best possible choice when you're working with, say, a strict budget, or you only have so many resources to go around. This is where a really powerful technique called linear programming comes into play. It's a mathematical way to find the absolute best outcome when your goal and all of your limitations can be described with simple, straight-line equations. Think of it like finding the perfect sweet spot inside a very clearly defined set of boundaries. For example, check this out. Imagine a factory with 2 different machines. Each one costs a different amount to run per hour, and each one uses up a different amount of labor and material. And of course, you've only got a limited supply of labor and materials for the day. Now here is the crucial part. You can define this entire puzzle with simple math. Your main goal is to minimize your total cost, but you have to do it while staying inside your strict limits for labor and materials, and you have to produce a certain number of items. Linear programming is a method that can take all of these rules and find the exact number of hours to run each machine to get the absolute lowest possible cost. Not a good cost, the perfect cost.
Okay, so we've got a method for finding a good enough solution really fast, and another for finding the perfect solution when you've got tight resource limits. But what about problems that are more like giant logic puzzles? The kind where the solution is all about making sure a complex web of rules is satisfied?
For those, we have something called constraint satisfaction problems, or CSPs. And really, any problem can be framed as a CSP if you can define it with just three things: a set of variables that need values, a set of possible values for each of those variables, and a set of rules or constraints that they all have to follow.
Sudoku is the absolute perfect example of a CSP. The variables, they're the 81 empty squares on the board. The domain, or possible values for each square, that's the numbers 1 through 9. And the constraints, those are the famous rules of the game. No number can be repeated in the same row, the same column, or the same 3x3 box. When you solve a Sudoku puzzle, you are literally solving a constraint satisfaction problem.
And what's really neat is that these constraints can be either hard or soft. A hard constraint is a rule that you absolutely cannot break. You can't schedule two different classes in the same room at the same time. But a soft constraint is more like a preference. It would be nice to have a morning class, but it's not a deal breaker. This lets AIs solve incredibly complex scheduling puzzles, satisfying all the hard rules while also trying to make everyone as happy as possible with the soft ones.
So we've looked at three really different ways that AI tackles these optimization puzzles. But so what? How does any of this actually impact our day-to-day lives?
Well, let's recap. We've seen local search, which is great for finding good, fast, good enough answers. We've seen linear programming, the powerhouse for perfectly allocating your limited resources. And we've seen constraint satisfaction, the master of solving complex scheduling and logic puzzles. Each one is a different tool for a different kind of problem.
And believe me, these tools are everywhere. They are the invisible engines that schedule airline crews to their flights, that plan the routes for delivery trucks to save gas, that manage factory production lines, and even balance our power grids. This isn't just theory, this is the backbone of modern logistics.
So the real key takeaway here is this. Optimization isn't just some abstract idea from a computer science textbook. It is the silent, logical force that brings efficiency and order to our incredibly complex modern world.
And all of this leaves us with a fascinating question, one that applies to AI just as much as it applies to our own lives. When you're faced with a really complex decision, is it better to aim for the absolute 100% perfect solution, even if it takes forever to find it? Or is it smarter to find a good enough answer quickly and just move on? The answer, it seems, depends entirely on the problem you're trying to solve.